Welcome to part 8 of this series of presentations on drillstring and drilling dynamics. My name is Ben Jeffryes. I'm now retired, but formerly I was a scientific advisor with Schlumberger. This is the first of 3 sections on bending and on the lateral dynamics of drill strings sitting in boreholes. For this first talk of the 3, I'm going to be looking at the effect of periodic touch points on the propagation of quasi-static disturbances, so mathematically statics rather than dynamics. There are more degrees of freedom for lateral deflection than axial or rotational, which creates a much richer static range of behaviour laterally than axially or rotationally. Knowing how deflection propagates through structures is crucial to understanding how drilling direction can be steered. Mathematically, the model I am using is a cylinder with periodic points which are either fixed or constrained. This is a simplified model for the tool joints in drill pipe or drill collars with periodic stabilizers. Obviously, in reality, these are not point contacts, but in studying lateral deflection, this is a very good simplification. I shall be looking at 3 cases, all with periodic touch points. Firstly, where they are fixed and there is no compression, i.e. no axial load on the pipe. This corresponds to vertical deflection of pipe, which is lying on the low side of a hole. Next, where the touch points could roll, again, no compression, corresponding to the horizontal deflection of pipe on the low side of hole. Finally, fixed touch points again, but where the pipe is under compression, i.e. axial load. The case of rolling touch points under compression will be covered along with vibrations in the final talk. We'll start with the simplest case, a constant cross-section pipe which can pivot at periodic points. This is an idealized model for drill pipe sitting on the side of a borehole at tool joints, or BHA collars with periodic stabilizers. Remember here I'm looking at motion in one lateral direction only, vertical for pipe lying on the side of the hole. The static beam equation is simply that the 4th derivative of the lateral displacement vanishes, so between the pivots, i.e. the touch points, the displacement follows a 3rd order polynomial. Gravity will add a bend to this, which is a 4th order term, but the system is linear, so this just adds on and can be ignored here. With the touch points at plus or minus 1, the displacement y in terms of the coordinate x has to vanish at the touch points, and so looks like this in general. As you can see, there are 2 degrees of freedom. Just as with propagating waves in periodic structures, we could write all solutions as a sum of periodic or exponential solutions, which we find by imposing these boundary conditions. The solutions are exponential, not periodic, and have a scale factor of -2 plus or minus √3. These 2 scale factors are inverse of one another, so what this means is that if we have an infinite pipe pivoting at periodic points, if we deflect it inside a span, the deflection in adjacent spans will be of the opposite sign and reduced by a factor of 2 plus √3, which is close to 4. All solutions for periodic pipe, both finite sections as well as infinite, with static touch points, can be constructed from these 2 solutions. One decaying to the left by a factor of 1 over 2 plus √3. The other decaying to the right by the same factor. Another way of thinking of these factors is to convert to an imaginary angle. If we regard lambda as the exponential of I times theta, then cos of theta is equal to -2. This may seem like an odd thing to do, but it enables a pathway to thinking about lateral dynamics in periodic structures. Let's look at an example. In this example, the beam has been pivoted at a touch point, x equals -1, leading to a large deflection close to x equals 0. The deflection profile in the next section is reduced by a factor of 2 plus √3 and is of the opposite sign. After 3 touch points, the amplitude is down by a factor of about 50. In general law about steering, there is the rule of 3, which is that whatever happens more than 3 touch points away from the bit doesn't affect steering, and this is the theoretical justification. But what about in the other direction? Vertically, for small forces, gravity keeps the pipe on the bottom of the hole, but in the other direction, horizontally, it can roll. In cross-section, it looks like this. I'm denoting the deflection by Y again. The pipe can roll around the hole with a rolling radius R. All the gravitational load of the span is borne at the joints, and this results in a point force, which corresponds to a step change in the third derivative of the deflection. The restoring force is proportional to the sine of the normalized deflection, which we can linearize, giving a step change in the third derivative of the deflection proportional to the deflection. Again, we look for exponential solutions, but now there are 4 equations. The rolling condition is the 4th equation. The restoring effect depends on one scalar, which I am calling mu, which is a ratio involving gravity, the rolling radius, and the mass and bending stiffness of each span. Remember, g is the component of gravity normal to the hole direction, so is proportional to the sine of the hole angle. This is quite easy to solve, at least in terms of what I called cos of theta before, the sum of the exponential factor and its inverse. Clearly, the exponential factors, lambda, come in pairs, so if lambda is a solution, then so is 1 over lambda. So there are 2 pairs of solutions, corresponding to the sign of the plus-minus term. There are 2 obvious limiting cases. If there is no restoring force, the factor mu is 0, and cos theta equals 1, so lambda also equals 1. The system is unconstrained, any deflection is undiminished. The beam may be moved to one side or rotated in the horizontal plane. The case we have just examined, fixed touch points, is the limit as mu tends to infinity, and the 4 solutions are now the 2 we had before, cos theta equals minus 2, and cos theta equals minus 4 mu. So in the limit as mu tends to infinity, there are only 2 degrees of freedom. As well as the solutions being inverses of one another, if mu is below 3, then lambda is complex, and they must come in complex conjugate pairs as well. This shows the amplitude and phase of cos theta, i.e. half of lambda plus its inverse, versus the restoring force strength, mu. But to get infinite mu onto a fixed length graph, I'm plotting lambda not against mu, but against mu over 1 plus mu. Cos theta in general is complex, so I'm plotting the absolute value and the phase. For mu equals 0, lambda equals 1. And for infinite mu, cos theta equals minus 2. So lambda is minus 2 plus or minus root 3. For mu equals 0.3, the magnitude of cos theta is 2, which is the same as the fixed touch point limit. Larger values of cos theta correspond to larger values of lambda, and hence greater deflection reduction between spans. So for mu greater than 0.3, there is greater reduction of deflection from one span to the next for the rolling system than if the touch points are fixed. For mu equals 0.5, cos theta is pure imaginary, and there is a pi by 2, i.e. 90 degree, phase shift in deflection from one span to the next. For mu equals 3, there is the greatest amplitude reduction between touch points. For larger mu, the deflection always changes sign from one section to the next. Let's look at some plots for what's actually happening to the pipe for different values of mu. In this plot, each span is length 1. The touch points are at the integers, and the span has unit displacement at x equals 0.5. For very low mu, the blue line, the pipe has moved in the same direction as the displacement for the touch points at x equals 1 and 2, and only reverses direction by the third touch point. As mu increases, the amount of deflection at the first touch point, and then in each span, decreases, until we reach a mu of 3, which is a minimum. For mu equals 50, i.e. practically fixed, the deflection in the first span is larger again. What values of mu are actually realistic? Well, for 5-inch pipe, 6-inch joints, 8-inch horizontal hole, mu is equal to 1. so a large mu range is covered in real life. The most counterintuitive point here is that in many situations in horizontal holes, horizontal lateral deflections, for which mu may be about 1, propagate much less far than vertical lateral deflections, which correspond to the fixed case. This was all for uncompressed pipe. We will cover fully what happens with compression together with lateral dynamics, but here is the solution with pivot points, i.e. fixed touch points. For consistency with usual conventions, I use the tension T as a quantity, which is minus the compression. K is then a kind of wave number that derives from the compression divided by the bending moment per unit length. The solution is shown top right. The limit as the compression tends to 0 is 2, so this is consistent with our earlier result. From the graph you can see that as the compression increases, the size of this cos theta term reduces, so there is less decay between sections, until when the sections are short enough, cos theta equals 1, and the pipe ends up in a sine wave through the pivot points, so there's no decay, simply propagation. Real pipe in world bores is chosen to be stiff enough that under normal compression that won't happen. Finally, a summary. Vertical displacements between touch points are reduced by a factor of nearly 4 between spans. What happens for horizontal displacements depends on parameters such as hole angle and size. In general, the reduction will be greater than for vertical displacements, and depending on the constraint, the displacement may or may not change sign between spans. We will look at what happens under compression together with dynamics in the final presentation. That's the end of this short presentation on periodic touch points. The next talk will be on buckling. As with all the presentations, any questions or comments can be addressed to the email address at the bottom right.